Hi, welcome to the JupyterCon talk on the Pulse Physiology Engine. My name is Bray. I'm a software developer at Kitware. I specialize in modeling and simulation architecture, integration of physics-based phenomenologies into distributed network systems, game engines, custom applications, basically exposing these complex algorithms to an expanded user base. So that comes to what I want to talk about today is usability and how we can utilize Jupyter to really reach a broad user base for some mathematical library that we're writing. Pulse is what I'm going to use as an example. It's a real-time C++ simulator, so right away, complexity is pretty high to use Pulse. You really need to have a high level of technical skill in C++ to use it. Exposing it through Python lowers that complexity. Python is really easy and user-friendly for a broader audience. So wrapping Pulse in Python is really beneficial to expand our user base. And then integrating it into Jupyter Notebooks really gets us a wider audience because we can bound a problem, we can walk it through, we can create a nice interface and really expose our library into an application setting and expand our base. Everything that I'm going to talk about today is open source and available at pulse.kitware.com. There's links to documentation and repositories, everything that I'm talking about. So let's start with talking about what Pulse is. It's basically a physiology library, which is the mechanical, physical, biochemical functions of a living system. Pulse operates from the tissue level up to a single organism. So backing Pulse is a pretty complex mathematical library implemented in C++ that calculates a lot of the fluid mechanics, diffusion, feedback mechanisms. It's a pretty complex model backing it. For our purposes, let's just think of Pulse as a black box. So one instance of Pulse is one human. The complexity that Pulse brings to the system is that it's just dynamic. It's continuous. So the user or application needs to always be advancing time. It's not a single calculation. It's multiple calculations, advance a minute. I want to inject a acute trauma. Let's see how the system responds to that. A hemorrhage can take minutes to actually show a physiologic response. So you have to continuously be calculating that. And any interventions take time. So the application always has to be walking Pulse with what they're doing. So our Nyquist frequency is about 50 hertz. So for every 1 second of simulation, we calculate 50 times. So it's a lot of data that we have to get out. Again, the Nyquist frequency allows us good waveforms, good valid data. So use cases for Pulse where Pulse integrates really well is game-based training because it has a frame rate that basically has time stepping. It's very syncs well with Pulse. Same with hardware testing. It's driving mannequins as the user interacts with mannequins. Pulse is interacting. This is real time. Same with medical devices. What I want to focus on today is how we use it for analytic studies because Pulse is very helpful in allowing users to experiment with different treatment protocols without exposing real patients and giving back a valid answer as to how this patient is going to react. So the use case that I'm going to talk about today is our study for multiplex ventilation. So earlier in the year, when COVID was a little less was more unknown, a lot of talk about ventilator sharing came up and how we're going to have to share a ventilator with multiple patients. And there was a lot of questions about how to do that, which patients could do that. And so we were approached by some critical care experts to run some modeling and simulation to see if we can figure out what parameters are best to match between patients that will give us the most successful ventilator sharing outcome as possible. So we wanted to also expose our model in a way that these experts could use. They didn't have a high technical skill, so we really wanted to create an interface for them to our model, and we did that through Jupyter because it's fast and quick. So doing that is from a C++ workflow is pretty difficult, but it's doable. You can download and build the source code. We have lots of examples. You can run the engine thousands of ways with multiple patients and run your parametric study and get data. But then what are you going to do with your data? C++ is not the place for data analytics. So that's kind of where we integrate into Python, and Python really allows us to do that. So how did we do that? we created a Python interface using PyBind 11. We did that through having a decent architecture where it's basically broken into components, where an application can talk to the Pulse Physiology Engine through a common software interface using a common set of data structures. So if we have that API and data structure layer that's basically encapsulated in mobile, we can really treat interlanguage communication as a client-server communication. So our front-facing API methods are written to take structures, and we implement our structures in Protobuf. And you can see some simple structures like hemorrhage and pneumothorax. And we utilize an object-oriented design pattern, such as the process action function can take any action, so it's inheritance. So again, this really simplifies our front-facing API and makes it structure-based rather than a lot of API methods for individual things. So once we have that C-style interface, we can basically copy it and create a string-based API. So instead of passing structures, we're passing strings. And since our structure system is backed by Protobuf, we can easily create JSON and binary strings utilizing that Protobuf library to pass back and forth between languages. So once we have that, wrapping it up in PyBind is really simple because that structure is the one that basically has the methods and it just accepts strings. So it's really short, really sweet, really easy to integrate into PyBind. But how do we generate those strings? That's where we basically take our simplified data model and interface and implement the structures in these various languages. It's a little bit of work, but it really adds to the usability of our SDK, and it does all the translation to and from Protobuf. So it's really simple class structures. It's not too hard to maintain, and it really allows us a better way to expose Pulse into these various languages. An alternative approach to binding is to use the scikit build system. That'll just it's a turnkey system for creating Python bindings for your C++ if restructuring your architecture is a bit overwhelming. So once we're in Python, we can basically do the same thing we did in C++. We can instantiate engines. We can create a bunch of different patients. We can run them through the Pulse engine. We can get back data, but we can analyze that data using a ton of data analysis packages available in Python and really see what parameters are important, which ones are not, and what the surviving cases are, and really have a very impactful analysis of our study. So how does Jupyter apply to this? Because we were pretty happy with the Python code to generate and analyze our data for a paper. But it's kind of limited to kind of an offline process, and it's good for just generating static images for analysis. We really wanted to engage the user. We really wanted to show our model and how it worked and its provability to these subject matter experts. And to do that, we really wanted an interactive experience. So we wanted to have some kind of user interface to do that. And again, Pulse is not an instantaneous calculation, so it's kind of real time. So what we ended up doing was creating this interface in Jupyter. It's very quick to set up, very easy. We used Binder to expose this, so subject matter experts did not need to get any kind of development environment set up. They could just go to a website and load up our interface and experiment with it. We used IPy widgets to create the sliders and the buttons, and that graph is made by BQplot. So the subject matter expert would come in, create a patient, 2 patients, set them up as similar, as dissimilar as they liked, run the simulation, and then they could adjust the ventilator settings to try and stabilize the patients, and see which patients could they stabilize, which ones could they not. So it really helped expose our model to an audience that did not have a lot of technical skill and get feedback from them. So this was our main goal, is to improve our model and get subject matter experts to buy into our model and understand it and contribute back and help us out, which in turn helped them. So the biggest challenge in implementing this was the real-time plotting in Jupyter. So that was pretty difficult. There was a decent amount of some Stack Overflow posts that I kind of went through. But again, Pulse is a bit different. The plots need to be updated with new data every 0.02 seconds. So creating a thread, pulling data from Pulse, putting it into a NumPy array, which BQplot would then take and render. So you can notice a little bit of jitter before, and so each array update has to render. So I was unable to decouple the rendering and data updates from each other. So if Pulse was called 3 times during one render cycle, each addition to the array kicked off a new render request. So each of those renders would occur, where I would rather, if 3 data points came in during a render cycle, I just want the next render cycle to include all 3 data points. I couldn't figure out how to get those to decouple. So maybe that's just a misunderstanding of asynchronicity of IPy widgets. That's kind of maybe we need better documentation on that. But I'm trying to figure it out. So hopefully I can have some lessons learned. The matplotlib was attempted, but pretty slow. Again, BQplot was quicker and quick enough. I'd really like to investigate Plotly and see how its real-time plotting capabilities work with Pulse, and how we can display these plots and graphs. Future challenges that I kind of want to address are integrating notebooks and coding and physiology all together in a way that really allows students to experiment dynamically with Pulse and apply it to their lessons, their applications, and be able to code their own trauma scenario very dynamically, have a library of widgets that can plot data dynamically. So as they're running, they can get pressure volume loops. These are very important for their medical analysis. So integrating more dynamic real-time plotting along with coding is our future plan. And again, as we're working on this, it is free and open source. You can come take a look at our repository and see how we're doing it, what we're doing, and give us some feedback. Thanks very much.